All right, everyone. Today we are going to continue with our polar equations. We're not going to focus as much on the graphing right now as we are really going back and forth and looking at how it relates to some of the other graphs. Maybe some of you have been asking yourselves, like, all right, these are all well and good when you have your polar graph, but what about a regular rectangular axis? Our Cartesian plane is what we call that. So what we're looking at today is how do we go from polar equations into rectangular equations. And then you'll see on Wednesday, we'll look how do we go from rectangular back to polar equations. And that's going to be something that's going to be useful in calculus next year. Sometimes the polar equation is easier. Sometimes the rectangular equation is easier when it comes to, doing the different calculus calculations and everything on it. You'll kind of have to make that determination which one is easier. So it's going to be important that you know how to go back and forth between both of them there. So taking a look at these here, what I want you to do first is just do really quick, pause this, and graph the three equations that I have on here. Just a quick review. You don't really need to show a lot of work. They should be pretty quick, easy equations. I'm going to do the same and pause it. All right, so looking at all three equations here, all three graphs, all three of them were circles. That's what we're going to start by looking at because we know a little bit about circles already here. So we graph the equation r equals 3, which is just a circle with a radius of 3 that in this case is centered around the pole. So we want to come up with the equation of the circle in rectangular form. This is actually something you probably did in geometry. You may not remember it, and that's okay. You don't need to necessarily remember it, but you might have come up with some equations for circles in geometry. What they are is they're actually part of a whole unit that we usually do, but we probably won't have time for this crazy year, called conic sections. If you think about a cone and you were to slice a cone in different places, that forms different conic sections. One of those conic sections is a circle. So if you were to slice the cone, if you think about parallel to the base of the cone, the circular side of the cone, that would form a circle. So that's why it's called a conic section. Again, we're not going to get really to that unit this year. We're just going to run out of time here. But that's just something to kind of have in the back of your mind. So if you wanted to write the equation of this circle in regular rectangular form has no theta and it has no r values in it. So it's just good old x and y in a rectangular form here. So if we wanted to graph that, really what we need to think about is we could pick any point on the outside of the circle. I'm just gonna, I don't know, pick some point up here. Doesn't matter where it is. I purposely, right now didn't pick one on, a pi over 4 or something like that. Just any point, and we can really make a triangle. And you'll see that we actually, this is going to be kind of similar to how we went through and proved our Pythagorean identities, because we're going to use some Pythagorean theorem in this. So if I call that point, that's just a point x, y, right? It has an x coordinate and a y coordinate. If I look at it right here, this length of the triangle would be x. This length of the triangle right here would be y. And this length, this hypotenuse right here would be our r value on this one here. So if we think about that, in this case, that r value here is 3. That is that radius of 3 on that one. So if we were to do Pythagorean theorem, that means x squared plus y squared is equal to 3 squared. And really, that is the equation of the circle in rectangular form. Again, you may have done that in geometry. You may not remember it from geometry. That's okay. But that's how we come up with our circle equation there. Pretty simple, I think. And you could obviously change the 3 squared to a 9. Really, we can do the same idea for this one. So here I'm going to look at the center of the circle. This is our center of the circle. And same thing, I'm going to pick some point on the circle and make our triangle here. Again, I'm going to call that point x and y here for x and y coordinates. This one also has a radius of 3, so that's still a radius of 3 here. Now, when I'm looking at this x coordinate still corresponds to the normal x, so that is still our x part of it right there. However, this is not just the y coordinate. If we think about it, this whole thing is the y, right? If I start down at the x-axis here and count up, that brings us up to that value of y. So that entire vertical distance here is the y. But if I look at it, we know that this part right here is 3. So that means, I know it's kind of hard to see in here. Let me see if I can maybe pick another color. But that means that this side of our triangle is actually y minus 3. So just to redraw that triangle, ooh, not a good triangle, but if this is x, this is our radius of 3. This side is y minus 3. Kind of take a second and think about why that makes sense there. So if I were to, again, do Pythagorean theorem, we have x squared plus a y minus 3 squared is equal to 3 squared, or 9. And this is our rectangular coordinates of our circle here. Okay, so if I tried another one, if I look at this last one here, so same idea again. I'm going to go from the center of the circle, pick some point, draw in our triangle here. So again, x coordinate and y coordinate. So this one, we know this one is a circle with a radius of 2. So we've got a little 2 right in here. Now this time, our y coordinate is just the y. So that vertical part is just y. But again, if I look at it, this whole distance is x, right? To go all the way out to that point, that entire distance, I should stop right here, is our x part of it on that one there. And so that means this little part is actually x minus 2. So if we look at that triangle, again, not a great right triangle here, sorry. That's y, that's 2, that's x minus 2. Supposed to be a right triangle there. If I look at that, again, that's going to be an x minus 2 squared plus a y squared is equal to 2 squared, or 4. Now, if you think about it, this is actually really just relating to all the other graphs that we've done. This is really h and k. Really, when we're looking at a circle, if we have a circle with a center of h, k, the circle equation is just x minus h squared and y minus k squared is equal to r squared there. And now this is something that, again, we probably don't necessarily remember from geometry. You may have learned it. We would have gotten more in depth into them going through our conic sections, but really, honestly, conic sections was only going to be probably about a week in class anyways. It's not a huge unit, but that's something that we would have talked about going through the different circles and the centers and that sort of thing there. But that's one way of kind of at least presenting how we could do circles, but we know not all of our polar graphs are circles. So we also have to think about what it would look like otherwise. So to do this here, really what we're going to do is we're just going to kind of generalize how to plot any point, or how to convert any equation into rectangular form. So pick any point, plot any point in the Cartesian plane. It doesn't matter where it is. Usually we like to pick one in the first quadrant just to kind of keep it simple and easy. We're going to make a triangle just like we did. Think about x, y, and r. So I'm going to pick any old point on here. Like I said before, I'm not going to pick one that like we necessarily know from our circle, so I'm just going to pick some random point right here. I'm going to call that point, again, x, y. So we're going to draw in our triangle. So that's my vertical, and that's our y coordinate right there. And then, oh, sorry guys, I think I hit something here. Come back. Okay. If I look here, this would be my hypotenuse. Down here is my horizontal. That horizontal is x. We have it perpendicular right here. And again, when I'm thinking of this, now I don't have any specific graph, but if the center is the pole and I'm going out here, that is what we call that r value. That r value is the distance from the pole right there. Okay, so what we're thinking about is really just going through and writing down some things we know about this. We know some trig stuff, and now we've actually done this before. Again, some of it'll look familiar when we proved our Pythagorean identity. Some of it you probably did when you were first creating the unit circle. So if we just use good old trig, I'm going to say, all right, well, the cosine of, I should call this angle theta right in here. That's our angle theta. Again, always with the initial side and then our terminal side over there. That's our angle theta. So the cosine of theta is, we know, the adjacent over hypotenuse, so x over r. Now, if we wanted to solve this any differently, I could multiply both sides times r, and r times the cosine of theta is equal to x. This one is going to be super important moving forward. Again, we actually probably already kind of knew that already. Think about on a unit circle, the x-coordinate is our cosine, because if we think about a unit circle, the r value of our unit circle is always 1. So 1 times the cosine gives you your x-coordinate. So that's something we actually already kind of knew. We can do the same thing with sine. So the sine, though, we know is the opposite over hypotenuse, or y over r. So again, if we multiplied both sides by r, we get r times the sine of theta is equal to y. Again, this one's going to be super important moving forward here. We could definitely do the tangent. The tangent is y over x. This one, we've done this already. We know this is how we do our tangent. We might use it every once in a while. It's probably not one of our main ones. You might have to use it every once in a while. It might be helpful if you have a tangent, but generally speaking, we don't use it as much. But the last one I'm going to write down that we use is just kind of general here. We know Pythagorean theorem. So x squared plus y squared is r squared. And again, that one's going to be important. So because those are our three main ones, those are the three ones I'm going to write down here. X squared plus y squared is r squared. That one's super important. I'm going to write down that x is r times the cosine of theta, and y is r times the sine of theta. Okay, so to go and take these three things, we're actually going to go back to these first ones and just kind of compare it back to that. Again, you're not going to have to do graphs on all of these right now, but just to at least look at it graphically and algebraically as well here. So I'm going to start with the r equals 3. So thinking of those three things that we use to be helpful. So x squared plus y squared is r squared. X is r times the cosine of theta, and y is r times the sine of theta. So to help in this one, we don't have any x's or y's in here, obviously, yet. That's going to be our goal on this here, but we don't have any sines or cosines or anything either. So I just have an r. So my thought on this one is, can we get this to be an r squared? So what if we square both sides on this? So if I square both sides, that gives me r squared is equal to 3 squared, or 9, right? Now we know r squared is equivalent to x squared plus y squared. And notice that just gives us the exact same thing. Okay, so just kind of another little proof of why that works here. Let's look at this one. Now, reasonably, we could try to square both sides, except we would end up with a 36 sine squared. Now, none of those things that we were just looking at have anything to do with sine squared. That's not really going to help us a whole bunch here. So again, we still want to try and get an r squared, but instead of squaring both sides, what I could do is I could multiply both sides times r. Right? If you multiply both sides times r, we still get r squared, but now I have an r over on this side. So I'm going to actually change the order of this. If it's 6 sine theta times r, I'm going to write it as 6 times r times the sine of theta, right? When we multiply, the order doesn't matter when we multiply there. Now, r times the sine of theta. The more you do this, the more you're going to be able to recognize here that r times the sine of theta is really just y. And then r squared, we know, is x squared plus y squared. And we actually achieved our goal of coming up with a rectangular equation. Now, you might be looking at this saying, well, that's not what you said before, but it actually is. Kind of go back and look at the one that we had before. Now, we just left it like this. This is actually more of like what we call kind of our standard form for a circle here in pink. But if I were to multiply this out, if I squared y minus 3, I'd get y squared minus 6y plus 9 right here. And take a look at that. The 9's would cancel out. So we'd get x squared plus y squared minus 6y is 0. And that actually is what we came up with. So these two are equivalent to each other. Both of them are the same thing. This way is kind of the more like conic section way. If you knew what the circle looked like and you knew what the transformations were, you know, this one moved up 3, then you could go right to that. But this one in purple up here is coming really from those going back and forth between polar and rectangular. So it's actually going to be kind of similar for our number 3 here. Again, instead of squaring both sides, I'm going to multiply both sides times r. So that gives us r squared. Again, 4 times cosine times r. I'm just going to rewrite it in a different order here. And that means r squared is x squared plus y squared. And over here, r times the cosine of theta is just 4x. And again, you can verify that those are actually exactly the same thing. Do you have to multiply them out? No. Again, this one was just one that we had come up with more visually from the graph, but you could multiply it out here just to kind of see that. Sorry, it's getting kind of sloppy in here. Plus 4. I sometimes write faster than the computer can handle here. And the 4's cancel out, so we get x squared minus 4x plus y squared is equal to 0, and that is the same thing. Okay, so again, that's kind of what our goal is going to be. So what you're going to be looking at, you won't have to graph on your homework, but you want to keep these 3 things in mind here. The x squared plus y squared is r squared. X equals r times cosine theta, and y equals r times the sine of theta. Those are the 3 big things, and that's what we're going to do right here. So we want to convert it to rectangular form. Big things to remember with rectangular form is there's no r and no theta. Okay, we don't want those in our final answers here. We only want x's and y's in our final answer, and other numbers, of course, within there. So if I have r equals 2, you might have in your mind, what does r equals 2 look like? You might recognize that, okay, that's just going to be a circle with radius 2. So that one might be pretty easy. But again, what I can think about is, since there's no sine or cosine in this, we really just want to get an r squared. So in this scenario, squaring both sides would be easy. So we get r squared is equal to 4, and r squared is just equivalent to x squared plus y squared. And this is our rectangular equation. This one, again, pretty similar to what we had done on the front side here. Again, instead of squaring on this one, it's not going to be helpful to have a cosine squared. Instead, we could multiply both sides times r. So r times r gives us r squared still. And normally, it's not always helpful to introduce the variable to the other side, but in this case, it is. Again, if you can think ahead that you are going to eventually have an r times either the sine or cosine of something, of theta in there, then you can think ahead and say, okay, r cosine of theta, that is x. Then r squared we know is x squared plus y squared, and we have the rectangular graph. Now, could you rearrange this? Could you reorder this? Yes, you could. You could, subtract the 3x, set it equal to 0. If you wanted to get it into more of that like kind of standard form for the circle with the center with the HK and all of that in there, you would have to do completing the square. Because we're kind of short on time with some of these, we're not going to mess with that. We're just going to stick with the x squared plus y squared equals 3x. You'll also notice as we go through this, you're not going to always get, or really many times often at all, get just like a y equals, because it's really not a function. If you think about this, this is a circle. Are circles a function? No, it wouldn't pass that vertical line test. So most of these, a lot of these are not actually circles here. So just something to are not actually functions, because a lot of them are more circular in shape there. Sorry about that. So just something to think about. You're not really going to get functions on here. Sometimes I will say you will. Take a look at number 3. Now, we haven't really talked about a cosecant or the secant on these yet. So hopefully your first thought is, well, instead of doing cosecant, let's maybe change that to one of our other functions. So for cosecant, I'm going to rewrite that as 1 over the sine of theta here. Okay, so none of them are being divided by the sine. So let's get rid of that divided by sign, and let's multiply both sides times the sine of theta. think my internet is slowing down here and it's making it all choppy. So that means on the left-hand side we have r times the sine of theta, and on the right-hand side we end up with just, oops, sorry, a 5, not a 1. 1 times 5, or 5. So hopefully you noticed right here, r sine of theta is y. And this is actually the equation y equals 5. Now you might be thinking, what the heck, y equals 5? That's a horizontal line. Yes, it is. If you were to graph this equation in polar, it is also just a line. If you graph that, try it on your calculator, try it on Desmos, it is just a horizontal line. Kind of interesting there. Okay, so that one actually happened to be a function. All right, looking at number 4, notice there already is an r squared. Okay, so there already is an r squared. If you see that, you can say right away, all right, I'm going to change that right away to x squared plus y squared. Unfortunately, on the other side, it's not so easy, though. Okay, we have 9 times the sine of 2 theta. We know because it's an r squared and it has that 2 theta, we know this one is the lemniscate, right? The figure 8 lemniscate there. Hopefully we recognize that. So thinking about this, okay, I have the sine of 2 theta. We need to go back and think through some of those identities. No, those don't go away. Sorry about that. I know some of you liked them, some of you didn't like them that much. But the sine of 2 theta, we could rewrite as 2 times the sine of theta times the cosine of theta. Just going to put in parentheses there. That's an identity. That's supposed to say identity there. Okay, that's just one of our identities within there. Okay, so now we've got a little bit more to think about here. So I'm going to rewrite this. We've got x squared plus y squared is equal to 18 sine times cosine. All right, in order to change that sine and cosine, it has to be r times the sine and r times the cosine. So that's really our goal. I want it to be r times the sine and r times the cosine. Now, I can't just, of course, magically multiply that in there, but you can multiply the right-hand side by r squared, which means we would multiply the left-hand side also by r squared. So now we have r squared times that x squared plus y squared. And on this side, I have 18 times r sine theta times r cosine theta. That says in sine there. Okay, so on the right-hand side, I have 18 r sine of theta is y, r cosine of theta is x, and over here on the left-hand side, r squared, I can write as x squared plus y squared. So I'm just going to clean this up just a little bit here. I'm not going to multiply it all the way out. You don't need to multiply all that out, but instead we could write it as, if you have the same thing being multiplied by itself, I'm going to write it as x squared plus y squared, that quantity squared. On the right-hand side, typically we just like to write it in alphabetical order, so I'm going to write it as 18xy. Now you do not need to simplify this anymore. This one I would say is one of those scenarios I said at the beginning of the video. In calculus, sometimes you'll want to use the polar, sometimes you'll want to use the rectangular. This is one that I would say maybe the rectangular might be a little bit easier. If you look at number 3, the polar might be easier on number 4, and number 3, the rectangular might be easier. So this one, the rectangular, is maybe a little bit more complicated, but if you did graph it, if you tried graphing it on Desmos, it will graph the lemniscate there. All right, two more to look at here. So in this denominator here, I have 1 minus the sine of theta. So we want to get rid of that 1 minus sine of theta in the denominator. So I'm going to multiply both sides times 1 minus the sine of theta. Okay, so times that r. So I'm going to distribute over on the left-hand side. So that's r minus r sine theta. And on the right-hand side, now I just have 4. Okay, so now I can look at this. R sine of theta, hopefully you recognize right away, is y. All right, we're getting close. We got rid of the thetas, we got rid of the sines and everything, but now we still have an r. So I'm going to get that r by itself. So I'm going to add that over here. Okay, and now again we want to get probably some kind of r squared. So instead of multiplying both sides by r here, that wouldn't help us because it would just bring in an r to the right-hand side that we don't want. This one, I can square both sides. So that means r squared is that quantity y plus 4 squared. And r squared is x squared plus y squared. And on the right-hand side, could you multiply this out? Absolutely, you definitely could. If you multiplied it out, you would actually notice that the y squareds would cancel. And what you'd actually end up with, this ends up being a parabola, which is kind of interesting considering you wouldn't have recognized that from the first equation here. But again, the y squareds would actually cancel out and you would have an x squared and a y in there. So it actually is a parabola function on this particular one. Kind of an interesting looking equation from the beginning. All right, last one you'll notice is kind of similar. Again, I want to get rid of that denominator, so I'm going to multiply times the 4 sine theta minus 2 on the right. Same thing on the left times that r. So I'm going to distribute that r through. So 4r sine theta minus 2r is equal to negative 16. Again, the more you do these, the more you're going to recognize r sine of theta is y. Okay. Again, we want to get r by itself really essentially here. One thing I want you to notice though is that they all have a common factor of 2 on here. I'm going to get rid of that. I'm going to divide them all by 2. So 2y minus r is equal to negative 8, just to simplify it there. Let's get r by itself. So I'm going to add the r and add the 8. So we have 2y plus 8 is equal to r. So again, this is not a scenario where you'd want to multiply both sides times r because we don't have a sine or cosine or anything on the left-hand side. That's really that only scenario there. So this is one of our scenarios that to get r squared, we would square both sides. So I have this quantity 2y plus 8 squared is equal to r squared. So again, could you multiply this all the way out? Yes, you could. I'm not going to make you on this one, but I do want to replace that r squared with x squared plus y squared. If you did multiply this all the way out, if we were doing our conic sections unit, you would actually see that this is an ellipse. It's another type of conic section. Basically, it's an oval. Ellipse is kind of like another fancier word for an oval in there. It's like if you were to cut a cone in kind of an angle instead of a parallel to that base there, that would create an ellipse on that one. So just something to kind of think about. So try these. On Wednesday, we're going to go the other way where you start in rectangular and we go to polar just to kind of compare the differences between them. All right, good luck on the worksheet and let me know if there's questions.